Before we check your answers to your trig assignment, let's listen to part of the unit circle song. This will be your punishment. If you don't remember the unit circle, I'll make you sing this song for me. Here's just a little bit of it.
I forgot the unit circle, trigonometry, sine, cosine, and tangent, and those trig identities. I forgot the lower half goes from pi until 2 pi. I forgot it all, and that's no lie. Think it goes like 7 pi over 6, hey! 5 pi over 4, hey! 4 pi over 3, hey! 3 pi over 2, keep going! 5 pi over 3, 7 pi over 4, 11 pi over 6, and then that brings us to the end, which is 2 pi.
And you can find a lot of fun numbers like that if you want to search for them. All right, so let's get going here. Our first questions deal with the quadrants. We want sine to be negative and tangent to be positive. Remember, sines are y coordinates in the unit circle, and tangent is the ratio of y to x. So if tangent is positive, y and x have to have the same sign. So the y coordinates are negative in quadrants 2 and 3, and y and x have the same positive negative value in quadrant 3. In B, we want the cosine of an angle to be negative. That's the x coordinates. So that would be quadrant 2 and 3. But we want the sine to be positive. That's the y coordinates. So that would narrow it down to quadrant 2. Theta is 11/6 pi is almost all the way around the circle. Remember that 12/6 pi would be 2 pi. That would be all the way around the circle. So we know this angle lands in quadrant 4. And negative 3/4 pi is a reminder that rotating in the negative direction, we rotate clockwise. So negative 3/4 pi also lands in quadrant 3. Question 2, the coordinate that gives the sine, we just answered a minute ago, is y. Cosine is the x coordinate, and tangent is y over x. So remember then that cosecant is the reciprocal of sine, and secant is the reciprocal of cosine. And of course, cotangent is the reciprocal of sine. So those are your unit circle definitions, and you should also, when the hypotenuse is not equal to 1, then you would use your SOHCAHTOA definitions. All right, convert degrees to radians. So remember, your conversion factor is that pi is the same as 180 degrees. So if these are common angles, I think you guys should recognize that 30 is 1/6. So that would be 1/6 of pi. Negative 135, I hope you remember this would be a 90-degree angle and a 45-degree angle, but both in the negative direction. So half of pi and then another fourth. So I hope you just recognize these as common angles. But remember, if it was not an angle you knew, you would multiply by your conversion factor. So we would want to cancel the degrees and end up in radians. So you could multiply by this fraction if you really were stuck and didn't remember. 120, I hope you see that as two 60-degree angles, so that's 2/3. Every 60 degrees is 1/3 of pi. And here we have 3 times 90, so every 90 degrees is 1/2 of pi. So I hope you didn't need a calculator for any of those. All right, these again, know your special triangles. 3/4 pi, that might look a little bit more like a 30, 60, 90 when it's a 45, 45. So 3/4 pi. So the two legs are equal. Now, I greatly prefer in calculus if you just go ahead and leave these in their pre-rationalized form. You probably in your algebra class spent a lot of time memorizing them in rationalized form. Here's exactly why I think that's the not the best way to go is because when you have to do the reciprocal, then students flip it over and rationalize it again. So if the sine is 1 over the square root of 2, then we know that the cosecant would just be square root of 2. So I think the pre-rationalized form would be my choice. And of course, when you do we could write here our definitions again in case this is really a review for anybody. But I hope that you know these quite well by now. Okay, so our tangent is our y-coordinate over our x-coordinate. So we're taking the first column over the second, but of course they're equal here. So the tangent, oops, better check my work here. Cosine, we're in quadrant 2, sorry. So I better put a negative sign here on the cosine, and that means I better put a negative sign on the secant. Okay, so the tangent is a negative, and the cotangent, the reciprocal of tangent. Negative pi over 2, we're rotating in this direction, and we're ending up down here at the quadrant angle. So our ordered pair is 0, negative 1. So our sine, cosine, tangent would be negative 1 over 0. So that's our undefined value. And secant is the reciprocal of cosine. So reciprocal of 0 is undefined. And cosecant is our reciprocal of negative 1. That would still be negative 1. And cotangent is our x-coordinate over our y-coordinate. And that's okay. That's not undefined. That's 0. 5/3 pi would be almost a complete revolution if it were 6/3. So there's our 30, 60, 90 triangle. It's tall. So the y-coordinate, the vertical leg, is longer. So our y-coordinate is the long leg of the 30, 60, 90, and the cosine is the short leg. And when we do ratios of these, the halves always cancel. So when we do the y-coordinate to the x-coordinate here, we'll get negative square root of 3. Secant is the reciprocal of cosine. Cosecant is the reciprocal of sine. And again, you probably have seen this always in rationalized form. I actually think it's much simpler. Just leave the square root in the denominator, not a problem. The reciprocal of tangent right here, again, leave it in pre-rationalized form. And pi is our quadrant angle over here, so we're at the point negative 1, 0. So this time our tangent is 0 over negative 1, but our cotangent, the denominator, would be 0. So here it's our cotangent that's undefined. And our secant works, but our cosecant, the reciprocal of 0, is undefined. And our negative 5, 6 pi is our 30, 60, 90 triangle over here. So it's short. So our sine is a negative, but a short leg. Our cosine is negative, a long leg. And the ratio of y to x, these halves cancel and the negatives cancel. So we'd have the square root of 3 in the denominator. So right away you might say, well, once I've done the tangent, let me flip that over right away for the cotangent. So whatever order you find this easiest. But don't worry about square roots in denominators. So if I was working too quickly and made a mistake there, I trust that you will catch it for me. All right, so some questions in other formats. Find another angle that has the same sign as pi over 4. Well, we could do coterminal angles, but that would be the same place. So I think this question is asking for this angle in quadrant 2, so I would go with 3/4 pi. A coterminal angle ends up in the same place, so let's not give that answer. I think that comes up later. And give the size of another angle that has the same cosine as pi. So pi is over here, and it has a cosine of negative 1. So another angle that has a cosine of negative 1, we don't have much choice here but to give coterminals. That is the only place on the unit circle is over here. So we would have to do 2 pi. No, let's try that again, 3 pi. Or we could go in the opposite direction. So In question 7, we need two values that have a cotangent that's undefined. So think cotangent. By definition, cotangent is the x-coordinate over the y-coordinate. So for it to be undefined, this question is saying where is the y-coordinate equal to 0? So the y-coordinate is equal to 0 at 0, pi, and 2 pi. So we actually have 3 answers. This says find all answers, so we've got to add our 2n pi's here. We could solve this by factoring this as the difference of two squares, tangent minus 1, tangent plus 1, or we could, since 1 is a perfect square, move it to the other side. But remember that when we take the square roots, we need to do both the square roots. So, of course, the square root of 1, you wouldn't write that. So where do we have tangents of positive 1? That would be here in quadrant 1 and here in quadrant 3, our 45-45 triangles. And tangents of negative 1 are in quadrant 2 and quadrant 4. Well, do you notice that these diameters are perpendicular to each other? So that tells you that each of these are pi over 2 units, jump away from each other. So I could start with just this first angle, pi over 4. Let me erase this work from up above here so you can see the answer. I'm going to start with pi over 4, and then I'm going to add every multiple of 90 degrees. But of course we're in radians, so we're going to add every multiple of pi over 2. So you could write it something like that, n pi over 2. So remember that n stands for every integer, positive and negative, because we could rotate in either direction. All right, another equation here, but it's already solved for us. So really we just want to find out where is the cosine negative, this is the long leg of a 30, 60, 90. So I hope you don't have to keep drawing these, but this is what I hope you have in mind. Those are the two places where the cosine is negative radical 3 over 2. But we also want the tangent to be positive. So of these two choices, we know that we're in quadrant 3. So now we've narrowed it down to this answer. And that answer is 1/6 pi more than a semicircle. So it is at 7/6 pi. Now, would there be anything wrong with saying that that's negative 5/6 pi? No, of course, those are the same angle. 7/6 pi and negative 5/6 pi are coterminal. And that's exactly what the next question is asking. Coterminal angles end up in the same place. So we want one positive and one negative. So we start with our 7/6 pi and we add a revolution. So that would be 7/6 plus 12/6. That would give us 19/6 for a positive coterminal. And you could continue, you could add another 2 pi and another 2 pi and so on. For the negative angle, we could say, well, what happens if we rotate in the other direction? So 7/6 pi minus 12/6 pi. We already talked about the fact in the previous problem that that's negative 5/6 pi. All right. I hope from our review of common functions, I hope that you can quickly graph a cosine function. I think the mistake students often make is drawing it a little higher than they should. So if this is our length of pi, don't get too carried away with your amplitude. It's not required. Let me see if I can get that back again there. It's not required to have your graphs drawn to scale, but it's nice if you can square up your x and y axis. So, and of course this is going to keep repeating this periodic function. So we notice that sine starts and ends its first cycle up at its maximum. And then that tells us what to do with the inverse. So cosine, well, let me first keep my red pen here and label a couple of these key points. So here we are at pi over 2, 0. pi over 2, and here we're at pi negative 1. All right, so remember, for an inverse, we have to restrict it to a 1-to-1 section. So we're going to take only the piece of the red graph that goes from the maximum to the minimum. So our restriction here is going to go from 0 to pi so that it passes both the vertical line test and the horizontal line test. And then the inverse function flips over the 45-degree line. It's a reflection. So the inverse of cosine is going to have this shape. I didn't draw that real carefully, but think what we know here. So our x-intercept on the red graph becomes our y-intercept on the inverse. And this red point at pi negative 1 becomes our point here at negative 1 pi. So keeping in mind that you want that flip over the diagonal line, and you need to restrict to a 1-to-1 section. All right, let's see if I can finish up quickly here. Question 13 is maybe better to answer first. So the period of a function is normally 2 pi. So remember that period is 2 pi divided by, not n, b. 2 pi divided by b. So here's our value of b in this problem. So 2 pi divided by 2 gives us a period of 1 pi. And the amplitude is the absolute value of a. So this value tells us we have an amplitude of 3. The negative part, the negative sign, tells us that we have a vertical reflection. Our graph is flipped upside down. So sine normally starts at the origin and goes up, so our vertical flip will start at the origin and go down. There's no phase shift here, so we're going to start at our same 0 point. So I'm going to choose, the amplitude is 3, so I'm going to use all the space I've got here. So I'm going to pick this value and call it 3. So that length should be about the same as pi. So I'm going to put pi at about the same place over here because that's our period width. So I'm going to chop it into 4 quadrants, and I'm going to start at the origin, and at the first quadrant I'm going to be down at the minimum, back to our center line, up to our maximum. So I hope that you now find graphing these transformations a lot easier than you did before. But don't quit here, please, until you've labeled your key points here. So just chop this up into 4 equal pieces. And that's all there is to it. All right, and what do we got yet? We've got a problem that doesn't quite fit in the unit circle. Negative 724. I'm just going to choose a point that looks reasonable there. And we always draw in standard position our right triangle going down to the x-axis. So our angle theta is actually outside the triangle, but remember this angle inside was called the reference angle. So I hope this sounds familiar to you, a 724-25 Pythagorean triple. So now the only difference is that we have to use SOHCAHTOA. Our hypotenuse is not equal to 1. It's not going to fit in the unit circle. So for the cosine, these are written in kind of odd order. So the cosine of our angle would be the horizontal leg to the hypotenuse. And I should put a negative 7 here to remind me that the x-coordinate in quadrant 2 is going to be negative. So horizontal to hypotenuse. The sine would be the vertical, that's positive, to the hypotenuse. The tangent is the vertical to the, or y to x, or vertical to horizontal, or opposite to adjacent, whichever you want to think of it here. SOHCAHTOA. And now we can just do our reciprocal. Secant is the reciprocal of cosine. Cosecant is the reciprocal of sine. And tangent, the reciprocal of cotangent. So remember that if it does not have a hypotenuse of 1, then you resort to your SOHCAHTOA definitions.